A fast food restaurant wants a special container to hold coffee. The restaurant wishes this container to quickly cool the coffee from 200 degrees to 130 degrees Fahrenheit and keep the liquid between 110 and 130 degrees Fahrenheit as long as possible. The restaurant has 3 containers to select from. Each one of these companies have different values for the machines. For example, CentiKeeper's company has a machine that cools the coffee from 200 degrees Fahrenheit to 100 degrees Fahrenheit in 30 minutes by keeping an ambient temperature and a constant temperature of 70 degrees Fahrenheit. The same applies for TempControl by lowering the coffee from 200 degrees Fahrenheit to 110 in 25 minutes and keeping a constant temperature of 60 degrees Fahrenheit, and hot and cold by lowering the coffee's temperature from 200 degrees Fahrenheit to 120 degrees Fahrenheit in only 20 minutes and keeping a constant temperature of 65 degrees Fahrenheit. In order for us to choose the best machine, we need to learn about Newton's law of cooling. According to Newton's law of cooling, the rate of loss or gain of heat from a body is directly proportional to the difference in the temperature of the body and its surroundings. Now that we know that, let's transform it into a function. We isolate temperature in one side of the expression and leave time in the other, and then we would take the integral of both sides. We move the natural logarithm to the other side as e to an exponent, and then we can get rid of the plus c by making it e to the c, but then that will just be a constant, so we can just leave it as c and we'll find out what that constant will be in a couple of minutes. And there we have it. That is our temperature based on time function. Time is the independent and temperature is dependent on time. So now let's work on finding out the values for the first company. We know what T of 0, T of 30 and the constant temperature is, so let's just replace the values and solve for C. Now that we know what C is, let's replace it on the original function and solve for K. In this case, we used T of 30 and use T as 30 in the exponent because we want K to actually have a value and not just be equal to 0. We take the natural logarithm in both sides to get rid of e to an exponent and just leave the exponent. And there we have it. So now that we have all the values, we can actually plot these functions. Each one of these functions represents a company, and therefore we create 2 lines, one that's red and one that's purple. The one that's red equals 130, which would mean the 130 degrees Fahrenheit that the coffee needs to be lowered at, and the 110 is the one that will represent the space between 130 and 110, and which is the optimal drinking temperature and will allow us to make our conclusions. Now, let's see at which point do each function reach 130 degrees Fahrenheit. But how do we find these values? Let's take a look at it. In order to do this, we will take one of the functions, in this case the first one, and we will equal it to 130 and solve for time, which will be the time it takes to reach 130 degrees Fahrenheit. And just like that, we just got the time it took the first machine to cool the coffee from 200 to 130 degrees Fahrenheit. And that's it. We can just do the same with the other two machines. The same process would be made, but with the line of 110, in order to find the time it stayed between 130 and 110 degrees Fahrenheit. Now, let's find those differences and let's see which is the most effective machine and which should we buy. And as you can see, the CentiKeeper's machine is the most effective one, as it lowered the temperature of the coffee from 200 to 130 degrees Fahrenheit in only 15.81 minutes. And it kept it in the ideal temperature for the longest time, 8.29 minutes. So if we were the owner of a restaurant, this should be the machine that should be implemented. Well, thank you for watching my video. I hope you liked it. I'll still do this type of animations in other projects and other classes, so yeah, thanks.